Okay, this is chapter 6, and we are doing exponential growth and exponential decay. Yesterday, we graphed and we saw the shape of an exponential growth, the shape of decay, how transformations can affect a graph with their H and their K. We saw, what domain, what happens with the range. We talked about the horizontal asymptote. So today, we're going to still have graphs of exponential growth and exponential decay, but we're going to translate into something that would be actually used in the real world. So, starting off, we are starting at example 8 of 6.1. Okay, first let me talk about these formulas up here. Growth factor. The growth factor means, first of all, growth is going to look like this, right? My A is still going to be my initial amount or my y-intercept. My rate, my R, so now there's not a B. Instead of the B, I add 1, and I add 1 to a percentage. So R is going to be represented as a percentage, pretty much for most of these problems. So if I can just refresh your brain, if I took a quiz and I got a 12% on the quiz, what was my decimal form of 12%? 0.12. So I'm moving my decimal 2 spaces to the left. So I want to make sure you all remember that. And this rate of increase is going to be your percent of growth. Time is always going to be measured in years. So 1 plus R is the growth factor. R is the rate. Okay. Here we go. In 1980, about 2,180,000 people worked at home. During the next 10 years, the number increased by 5%. So 5% is going to be that 0.05. I'm going to write, because I've got to fill in an A, W equals, workers equal, A, 1 plus R to the T power, time. My A is going to be 2.18, and this is expressed in millions, and my rate is going to be 0.05. Okay, so instead of A, you're going to put 2.18. Instead of R, you're going to put 0.05. And time, during the next 10 years, it increased by 5%. So I'm wanting to know how it looks until it gets to 10 years. Like at year 2, what was the number at? And then I'm going to graph this information. So I'm not going to fill in 10 right now. Okay? So we need to label our graph. Okay? This is going to be the years. And I'm going to go, you guys listen. If I have a blank graph, I need your help on this one. If I have a blank graph with 20 squares and I need to make this last 10 years, what would you like me to do with my numbering? Call what's the scale of the graph going to be? Yeah. Go by twos. Every 2 boxes is 1 year. So label it, please. 8, 9, 10. Okay. So there's that. And then I need to label my y-axis. This is going to be millions. The number of people. And I just want to go, because I already know the answer, I'll go 4 million. I want my graph to reach 4 million by the top of my y-axis. So if I want 0 to be here, 0 million, 0 people, and I want the top to be about 4 million up here somewhere, there's 20 boxes, and I want to go to 4 million. How many boxes should 1 million be? 5 would be fine. Okay. 1, 2, 3, 4, 5. That's 1 million people. 1, 2, 3, 4, 5. 2 million people. 1, 2, 3, 4, 5. 3 million people. And then I'll do 4 million just somewhere up here, whatever. Approximately that. All right. Here's my graph. So I have to set up my empty X and Y axes to fit what I'm doing. Okay, now I'm actually going to do the math, and this is when a calculator comes in handy, because I want to know approximately during the next 10 years it increased by 5%. So I could do like 0 is going to be my y-intercept. What's my y-intercept again? 2.18, 2.1 million people. That means I'm going to start like up here, approximately my y-intercept. My graph starts up there. My other numbers I could do like 1 or 6 or 10. I'm not going to do them all. That would be ridiculous. Too much work. Just pick a couple numbers. Okay, you need a calculator for this. Here's what you're going to do. Okay. I'm going to do 2.18 times the quantity, 1.05 to the t power. This calculator is awesome because I can just enter everything and it does all the math. If you have a cell phone calculator, I'll show you how to do it on the cell phone, or just like a basic one. You must do 1.05 to the first power. You have to do that first and then multiply it by 2.18. So that's my decimal, obviously, times my initial amount, my A. 2,280,000. So on any normal calculator, you must do the exponent first. Let's do 6. 1.05 to the 6th power. And then multiply it by 2.18. You don't want to round because we're talking about people. So you can't like round people. Okay. Times, so that's my parentheses, times 2.18. 2.92. And I'll just do that. Now I'll go 10 years. 1.05 to the 10th. And then multiply it by 2.18. 3.55. Okay, so I can plot those points, and this is going to make an exponential growth function. Over 1 up 2.2 something, it's maybe like there. Over 6 up 2.9. Over 10, 3.5. So this is my exponential growth function. And it'll slowly increase. Okay. When will there be 3.22 million people? So now it's asking me to figure out the years. When will that be? Okay. I'm going to set up. I know the answer. I know my W is 3.22. And my equation has everything except for the time. So I'm going to put my equation 2.18, 1.05 to the t, right? And then, okay, I slowly need to isolate t and figure out like what this would be, you know? So, any thoughts on what I would do first? Okay. You're going to divide by 2.18 to slowly isolate things. Okay. Oh, sorry. Here's my calculator. 3.22 divided by 2.18, 1.4. So on one side of the calculator, I have 1.47. I'm not going to round crazy. 1.05 to the t power. Now, 3.22 people is approximately, because look at 10 years. 10 years was 3.5. So this is going to be really close to like 9 or 8 years, something like that. So I'm going to play around and see. Let's try, I guess, let's start low. Let's try 8 years. So 1.05 to the 8th. Let's see what that equals. Times 2.18. Yeah, it worked out perfect. 3.22. So 8 years. 8 would be it. Because look, 1.47 equaled 1.05 to the 8th. So I knew that that was good also. Okay. All right. Let's practice 9. A ring was purchased 20 years ago for $500. The value of the ring increased by 8% each year. So let's label everything. What's A going to be? What's R? And what's T? All right, looking at this, my equation is up on top. What's A going to be? What am I starting at when I bought the ring? $500. Very true. What's the rate that it increases by? 8%. 8%. Just make it 0.08. And the time. Well, 20 years ago I bought it, and now today 20 years has passed, so the time is 20. All right, set up the equation with your group and work it out. Go ahead. Okay, ready? What was the equation that you wrote? Somebody tell me the formatting of it. Go ahead. 1 plus 0.08. Okay, good. I need to make this just 1.08. Okay. Did you get $2,330 approximately? Yeah. Okay, good. And that is true. Like diamonds do increase in value. So you guys know for your life. All right. Jump ahead to 17. This is the last one we're doing. Decay is when something goes down. Decrease. And there's a subtraction sign in the middle. Guys, we're being recorded right now. All right. So if something loses value, we're going to put a minus sign in the middle. There are 40,000 homes in your city. Each year, 10,000 of the homes are expected to disconnect from septic systems. Do you guys know what a septic system is? It means that in the ground below your house, you have a giant tank, and that's where all of your bathroom goes when you flush the toilet. And these septic tanks were installed early on when they were building homes. But what started to happen is they would get full or they would deteriorate. And so then it would start leaking under your home. Yeah, pretty exciting, huh? So that's when the sewer system started. And that's when you flush your toilet, it goes out through the sewer lines to your sewer treatment plant. And I don't know. I don't know what happens there. We don't have to talk about it. I don't know. But anyways, a septic tank, a septic system would be like something that's outdated now. You would never buy a home and they're like, oh, you don't have a sewer line. You have a septic tank under your house. And you would say, no, I'm not buying this house. Okay. So here we go. This is decay because 10% are being removed. You start with 40,000 homes. I am decaying. It's 1 minus the percentage, my R, 0.10. How many years? Oh, I don't know. I don't know how many years. Anyways, 1 minus 10 cents. $1 minus 10 cents, basically, right? 90 cents. So what's going to happen is a graph would be something. So I would start. Obviously, this is my y-intercept, guys, 40,000. You need to figure out how you're going to scale your drawing. I'll just tell you because I'm going to be teaching right up to the bell. I'm going to do it by 10,000s. How about? 20,000, 30,000, 40,000. Okay, that's my y-intercept. And I'm decreasing. So I could say, oh, let's just practice. Let's say 5 years. And then maybe 15 years. So on your 40,000, this is how the calculator works if everything's perfect about it. Like it's a scientific calculator. I can put everything in order. You cannot do this on a basic calculator or if you're trying to use your cell phone. 5 years. How many? Only 23,000 have septic tanks. Then 15 years. That would be 8,000. So with this data now, I can get an approximate graph. Let's see, 5 years, 10 years, 15 years. I'll just, whatever, approximate years. 5 years is 23,619. 15 years was 8,000. Something around there. So this decay model goes downward and it keeps getting smaller and smaller. And at this point, Fullerton was created a long time ago. Guaranteed, some of these homes in Fullerton have a septic tank sitting under the home. And it's just abandoned. It's just sitting there full of, and it's just there. But no one digs them up. You don't do that. You don't dig them up and remove it. No, you just let it sit and be there for the rest of time, I guess. Okay? But that was the solution. When people were building homes, they're like, where are we going to put all the waste? Oh, okay. So, we need to stop there just due to time. So let's talk about your homework.